paper. The key here is there are 3 planets in this system, and they're all terrestrial sized. This is one of the validated systems. It's statistically validated, so we don't know the masses yet. But we do know that they're inside the habitable zone, not in the habitable zone. Okay, so where does that lead us? That leads us to the first habitable zone TESS planet. Can't say that word. This is GJ 357 B, C, and D, another triple planet system, with the D planet, the outermost planet, being in the middle of the habitable zone. This is closer at 31 light years away. And then finally, the TOI 270 system, yet another multi-planet system. These are the ones that are easier to validate because we can see transit timing variations in the test data, and we can basically use the existence of the 3 planets to help prove that they must be planets rather than background eclipsing binaries. There's 1 rocky super-Earth in this system and 2 sub-Neptunes, and these are orbiting an M-dwarf star, a very small star. So they're so close in, though, you can see if the graphic comes back around there, they're much closer in even than Mercury in our solar system. And no, we do have one more. So one of the initial discoveries was also LHS 3844b. It's a hot Earth. It's hot Earth because it's in a half-day period, and it's 1,000 degrees T effective of the planet, or TEQ. But what's interesting about this planet is a recent paper that came out, which did use Spitzer photometry that observed an entire orbit of the planet around the star. And so what you can see here is the light curve. The little white symbols are the actual data. The blue line is the model. So this very deep dip here, the dimming of the star, is when the planet is at phase 3 here. It's passing across the face of the star. And then you can follow the numbers. They match up around through here, and as the light curve moves along here. So what you see is when it comes out of transit and starts to orbit around the star, you get a little bit of a brightening. And that happens because more and more of the day side of the planet is starting to face Earth. So we get the combination of the day side of the planet and the star's light together, and that causes the combined light curve to increase until the planet gets to the star and passes behind the star. When it passes behind the star, we get this sudden drop back down to the baseline level here. And then as it comes back out the other side, flux back up and then decreases as it comes back around to transit again. So how do we, what can we learn from this? Number one is, if the hot spot on the planet, if the day side of the planet has a hot spot that's not exactly centered with when it's coming around to go behind the star, we can deduce that the atmosphere on the planet is circulating and causing the hot spot to move off to one side or the other. So what this paper did is found that the hot spot is indeed right in the middle where it should be. In other words, there's no skewing to this signal that comes up and goes back down. So the conclusion is that there's no thick atmosphere. It doesn't mean that there's no atmosphere at all, but there was no thick atmosphere that could be detected. That was one of the big bang announcements at the TESS conference earlier this year in August. So that is called a phase curve. This observation and the photometry of the entire orbit we call a phase curve. Normally that's done, Spitzer is a near-infrared instrument, so the wavelengths are well beyond what we can see. that's because the planet is much brighter in the infrared relative to the star itself. And so we get more relative flux from the planet compared to the star, so it makes the signal to noise of the planet higher. That's normally hard to do in the optical and the infrared just outside the optical where TESS observes. But TESS has such high precision that we can even see for very hot planets, we can see phase curves in TESS. These are actual TESS data. Okay, let's revisit our zoom out image here. Now, the mission is just getting started as far as planet discoveries go. So what I've plotted here is red symbols indicate the actual planets that have been discovered already. And the yellow symbols are planets that came out of a simulation that we did prior to launch of the spacecraft, just to give us an idea of what yields to expect. So we're starting close in here. You're looking at 30 light years here. We should find about 8 to 10 planets within 30 light years. You can see just outside, we already have 3 planets showing up here, probably 40, 50 light years, the ones that we discussed. And now we're going to zoom out. You can see the blue dots here now are the Kepler ones, the ones that are mostly very far away. So you can see we're already out of TESS space and back into Kepler. So you can see how much closer the TESS planets are than the Kepler planets on average. Okay, I'm just going to highlight some non-planet science because there are people doing work. I don't understand all of this, so I'm not. Don't ask me too many questions about this part. But there are amazing things being done with the TESS data that I would have never dreamed of. John, actually, Dr. Kilkoff does a lot of this work, and if you're interested, I also wanted to mention that I believe that you have all of the FFI data here locally on campus, right? So you don't have to, it can take a long time to download the FFIs, but John has it locally on the servers here on campus, so it's yours to use. People study flares in M-dwarf stars. You can see an example, 2 examples of flares that were observed by TESS there. Astroseismology, I know even less about this topic other than we're measuring, they do a Fourier transform of the light curve basically, and you can determine the vibrations in the star, which can tell you things about the mass and other things that I don't even know about. Supernovae. These are supernovae that were discovered early in the TESS mission, published by Michael Fasnall. Oh, this is a cool animation here. This shows so many things, so please pay attention to this one. This is one time series from the FFIs, okay? First, you can obviously see the comet. You can see across the top there what we're going to see. You see Neowise Comet C 2018 N1. You notice how the tail direction changes as the solar wind moves it around. Variable stars are everywhere. It's like a Christmas light show if you play the TESS images in a time series movie. So you can see the star flashing off and on. Same over here. Dr. Kilkoff has produced some amazing time series like this with some special software that he's developed. Oh, this is cool. Somebody figured out that, I don't know if you can see it from there, but there's a faint wisp of light moving through, and that's scattered light off of Mars. And then check out these asteroids. You don't see them in a linear plate, but now if you move back and forth, do you see the asteroids moving back and forth?
That's so cool.
This is just one time series from TESS. So much more than planet science going on. There's it comes to this chart. All of these data are public. Like I said, John has the FFIs here. Play with them. You can load them up in your favorite FITS viewer. If you don't have a favorite one, download the one I wrote called Astro Image Shade. You can load them up and play them like a movie and see what you find. Load them into your favorite analysis tool. See if you're studying a particular region of space or star, there's more than likely data on it now with a time series every 30 minutes. Oh, and both the 2-minute postage stamps are there too, so if you need higher time resolution. Okay, so what's coming next? The good thing is, especially for me, it means my job lasts at least 2 more years, NASA has recently approved back in the summer 2 more years of the TESS mission. So we will be running now at least through 2022. I'm not aware if there's at first we thought we were going to just resurvey everything exactly the way we did the first 2 years to get more data and a longer time span. But I think we're looking at some different